All right. So now you know a decent amount of things, right? Now you know one, how to calculate concentration with moles over liters, so you know molarity. You know how to determine if something's a solid or if it's going to stay aqueous in reaction. You should know how to balance the chemical reaction. And you should have practiced limiting reactants from the last unit and figure out which chemical is going to run out first. Now, all of these are going to be very, very useful in these next types of problems. So the problems are going to begin to get a little bit more complicated. They're going to get more difficult, and they're going to require you to access skills that you learned in the past. So it's very important that you continue to work, continue to do these types of problems, continue to read the book, continue to try. If you at some point begin to kind of give up, it's going to make a little snowball effect and kind of get overwhelming. But as long as you continue to do this and just push yourself, you will be okay. All right. But let's whoops. The next thing we're going to do is solution stoichiometry. So figuring out how things react, or how much of things react, or how many things are needed to react, or how much stuff will we be able to make, or what is the percent yield, or how many grams or particles will we make. All of these things we're going to be using. We're going to be using solutions and stoichiometry to get there. Okay. Now, there's a couple of like guidelines to do this, but I suggest you don't look at guidelines. I suggest you try to figure out in your head, how are you going to approach this problem? What information do you know, and how can you get to that information you know? And over time, you won't need a reference. You won't need this stuff right here. I highly encourage you to not use this. I encourage you to not use a mole map and actually just try the problems. All right. So let's check this out. So for problem 4.7, calculate the mass of solid NaCl. I believe this is a problem in your book. This is example 4.10 in your book on page 138. Now, the problem is calculate the mass of solid NaCl that must be added to 1.50 liters of a 0.100 molar AgNO3 solution. So you have 1.5 liters of silver nitrate. So inside the silver nitrate, there's inside this solution, there's Ag floating around and there's NO3 floating around. What happens is someone's got some salt. You have some salt. And you pick up this salt and you're going to add it inside the beaker until all the silver reacts and it comes down into solution. This is a way of cleaning, of purifying your solution, or getting rid of metals. Let's say you have drinking water and you don't want to drink any silver. Well, you can add stuff in there to make a solid and force it out, and then you can clean up the solid, and your liquid is now cleaner. It has less stuff floating around it. So, or less toxic stuff floating around it. So just keep that in mind. Now, which one's solid, which one's liquid? Whenever Na or NO3 are present, automatically you should be thinking that's solid. No, that's aqueous, foo. Now, whenever Ag comes out, you should be like, oh, is that a solid? It's a solid. Let's check it out. But this is a chloride. Chlorides are soluble in water except with those, and that's one of them. So that's a solid. Now, I'm going to skip the complete net ionic equation because I know what the important part is. This is the important part. And I know that AgCl is made of Cl minus and Ag plus. All right. I just like having this as a little reference. I actually don't think we're going to need that net ionic equation for this. All right, but let's check it out. Calculate the mass of solid NaCl that must be added. Now, I don't like that piece of information. The 1.5 liters of AgNO3. Remember what I said. If you have molarity, which is big M is equal to moles over liters. The important thing is the moles. The moles tells us the amount of particles that are in there. So if we know the moles of Ag, well, we can determine how much Cl we need. And if we can determine how much Cl we need, we can determine how much NaCl we need. So that seems to be the thought process here, the guidelines that we're going to use. So what we're going to do is we're going to figure out how many moles we have. So remember this formula, big M, so 0.100 molar AgNO3 is equal to, well, we don't know the amount of moles, so we're just going to say X moles of, what is it, of AgNO3. And then underneath, we have 1.5 liters. So how do we get the moles on its own? We multiply both sides by 1.5 liters. Multiply both sides by 1.5 liters. And what we're going to get is the moles of AgNO3. And I don't have my calculator. So this is easy. So this is 0.15 moles of AgNO3. All right, so instead of dealing with molarity in liters, we now know the number of particles. We know 0.15 moles of AgNO3. So what we really want to find out is how much NaCl we need. All right, so we need to figure out how much NaCl. So I'm going to erase this. Hopefully you don't need this anymore. All right. So if we have 0.15 moles of AgNO3, we can determine how much NaCl we need. I think I said it. I think my plan was a little bit longer than this. I said we were going to go to Ag plus, then Cl minus, but we don't really need to do that. Let me see. So how do we go from moles to moles? It starts with an M and it rhymes with ol ratio. That's right, you got it. You got it. I know I heard you. I heard you all the way over here. And we know that 1 mole of AgNO3 reacts exactly with 1 mole of NaCl. So this is going to give us 0.15 moles of NaCl. So this cancels and this cancels. So now we have 0.15 moles of NaCl. But we are looking for mass. We're looking for grams. So we need to use the molar mass. We know that 1 mole of NaCl, so Cl is 35.45 and Na is 22.99. I'll just Google the molar mass. Molar mass, NaCl, 58.44. I did that in my head. All right. So 0.15 times 58.44, and it gives us 8.77 grams of NaCl. All right, so there we have it. Now, I want to show you that your book did it a little bit differently. If you look at the example from your book, the example from our book, where are you, book? Hello, book. Throwback to other video. How fun. Oh, if you get a chance to read this guy's smart. What a nerd. What a nerd. This guy, he's a nerd. I'd read about him. Interesting nerd. All right, let's keep going. We were looking at, we've covered a lot. We're looking for 4.7. Mr. Sanchez, why do you ever have this ready for us? Why are you wasting our time? How about you shut up and keep watching the video? Don't show this to your parents. Because they're going to be like, your teacher's telling you, shh, shh, all right, gentle, shh, shh. All right, so check it out. Check out the way they've done it. They went to moles of Ag+. It's not necessary to go to moles of Ag+. So there's more than one way of solving these problems. That's why I tell you don't really follow the guidelines, because the guidelines can sometimes just confuse you because you're like, I must do this step. I must. When in reality, you don't. Right? For example, they broke it apart to AgCl. They figured out moles of Ag+. I didn't have to, because I realized that the relationship between AgNO3 and NaCl, we could have just used that, so that's okay. You could go from Ag+ to Cl- to NaCl, but it's, to me, I don't know. I think it's kind of pointless doing that. So always be mindful of that. And I don't know if you guys want me to do another problem. You guys can stop here. You guys can stop watching it here, but let me take a look at maybe another problem with you guys, so you guys aren't like, Mr. Sanchez only does some problems with us. So let me check out. I think 72 might be a good one. Let me erase some of this. Go away. I do not need you. All right. Let's check out 72. But if you want to, you can stop. I don't think you need me. I think you're good. You're good. Let me move me. Where do I move me? I'll move me here. All right. When aqueous solutions, Na2SO4, so Na2SO4, as soon as you see Na, you should be thinking it's aqueous. It's reacting with Pb, NO3, 2. As soon as you see NO3, what should you be thinking? That's right. When is he not going to say this? Never. All right, so we are going to make Pb, and this Pb has a charge of +2. SO4 has a charge of -2, so it's just going to be PbSO4. We don't know if it's a solid yet, so let's hold off on that. We know NaNO3 is automatically, that's right, I've said it before, I'll say it again, it's a aqueous, solid, gas. All right, so sulfates, if there's a Pb +2, it is a solid. So let's write that down right here. It's a solid. All right, little quick balance. There's one NO3 right here, but we should have two. There's two NAs. There's one SO4, there's one SO4, there's one Pb, there's one Pb. Awesome. Awesome. Now let's check out the problem. Calculate the mass of PbSO4 formed when 1.25 liters of this and 2.0 liters of Na2SO4 are mixed. So this problem gives you two pieces of information. That complicates our life just a little bit more. But you've done problems like this before. You've done labs like this before. Let's check them out. One of these is a 1.25 liters of 0.500 molar, and that's lead nitrate. And the other one is 2.00 liters of Na2SO4. And basically what happens is one of them gets poured into the other and the reaction happens. But this is four values. We got volume, moles, molarity. Let's simplify it and turn them both into moles. So remember, your moles is equal to your molarity times your volume. So The moles is equal to, let's do the lead nitrate first, times 1.25 liters. So let's label it PbNO3 2. Sorry for my ugly writing. I want to keep the video short and short. It's like 30 minutes. Here I am making mistakes. Don't make mistakes like I do, people. Make better mistakes. You guys make the same mistakes I am. That means you're not paying attention. So this one is 0.025 molar times its volume. So the moles times its volume will, the molarity times its volume will give you its moles. So this is going to be 5.5 times 1.25. Oh, that's not way off. 0.625 moles. And that's moles of Pb. I know, this is a little annoying, but that is life, people. That is AP chemistry. You chose this life, not me. Oh, I also chose this life, but that's okay. Now this is moles of Na2SO4. So now instead of relying on like the net ionic equation or anything smaller than that, and instead of relying on liters and molarity, we deal with old moles. That's why moles is so important. That's why we did so many problems with it, because once you can get to moles, you can figure it out. You're in, like, the goal is to make moles your home field advantage, right? Where you're familiar grounds for you. All right, now let me hello, move mole, bro. I've been craving some mole. Yo, if your mama or anyone you know makes some mole, extra credit for sure. A+ is for you. I'll take the AP test for you. No, I can get fired, I think, for even. Nah. Anyways, once we're at moles, we can then determine what can we determine? We can determine anything. We can find what we want. We want to find the mass of PbSO4. So when we're looking for mass, we are looking for grams. Hello. We're looking for grams of PbSO4. So we got PbNO3, we got moles of this, so we can go to grams of this. So let's go ahead and do that. And we know that 1 mole of PbNO3 will make 1 mole of PbSO4. That's the mole ratio. And we can do that with Na2SO4 as well. We know that 1 mole of Na2SO4 will produce 1 mole of PbSO4. Mr. Sanchez, where are you getting this information from? Oh, that's very, very simple. We get that from the coefficients of our balanced chemical equation. That is our mole ratio, okay? Now, we don't want moles of PbSO4. We want grams. But we know that 1 mole of PbSO4 is equal to, hey Siri, what's the molar mass of PbSO4? Siri, you are useless. I don't mean to. All right. Oh. If it confuses you that I'm doing both of these sections at the same time, please let me know so I can ignore your request. So 303.26 grams. So that's the molar mass of PbSO4. Now, why am I doing 2 separate problems? Well, the reason I'm doing 2 separate problems is because we're trying to determine which one of these is going to run out first. This is a limiting reactant type of problem. One of these runs out first. It kind of looks like this one's going to run out first, but I just like doing both for the peace of mind. All right. So let's do this. Whenever you do limiting reactant, you got to do the problem twice. One for each starting thing. Whichever one produces the least, that's your answer. So 303.26. This makes 189 grams. 189 grams of PbSO4. We got 3 sig figs, so that's got 3 sig figs. Oh, that should have had an extra 0. Whoops. And then this one over here makes 100. Oh no, this one makes 15.2 grams of PbSO4. So one of these ran out first. So which one's the correct answer? Whichever one is lower. The one that made the least, because that's the one that determines when the reaction stops. So we have 15.2 grams of PbSO4 that were made. Now, problems like these are going to be very, very, very common. So get used to them. Get used to them and practice them. And don't get scared to make mistakes. Go and make those mistakes. Go and check your balanced chemical equation. Go and check your formulas, because you don't want to make mistakes. And if you do make a mistake, it's okay. If you make a mistake, straight line through it. Do not erase it. Do not cross it out. Do not scribble it out. Just a single line across is all I need. Okay, do not scribble it. If you scribble it, I'm taking all your points away. Okay, you're gonna taking extra points away. I gotta see your mistakes. Show me those mistakes. Show me your thought process, because that's the most important thing. Okay, peace out, people. Do these other ones. You got a lot of work to do. Peace out.